So last time I showed you some interference and diffraction experiments which tell very clearly that light is a wave phenomena. But what kind of wave it is? People say it is electromagnetic wave. So when you have light, you actually have electric field and magnetic field which change with time at every place. So the field, electric field and magnetic field, they constitute this what we call light. So if the medium is homogeneous and dielectric medium, insulating medium, no conductivity, then the electric field, the magnetic field and the direction of propagation, they are perpendicular to each other. If this light is confined in some kind of boundary, then this is not guaranteed. So in general, what we will have is electric field oscillating in the plane perpendicular to the direction of propagation, and magnetic field also in that same plane perpendicular to the direction of propagation and also perpendicular to the electric field. So that is how the electromagnetic waves in general look like. Now there are some materials, and in these materials which we call polarizers, which I will be doing experiments with in this session, there are structurally there are some specific directions, so that if the electric field is parallel to those directions, light transmits, it goes through that material, through that medium. But if the light goes with electric field perpendicular to those specific directions, then that light is blocked. And if the electric field is, it makes a certain angle with that specific transmission direction, then the component of the electric field along that direction is transmitted, and transfers to that is blocked. And the most interesting thing is, whatever be the direction of electric field before entering this polarizer, the electric field direction after going through this polarizer will always be parallel to that specific transmission direction. And this has lots of beautiful demonstration experiments. The light that we generally get from the sun or from a candle or from a filament bulb or from CFL, generally the light that we get from these sources is unpolarized. What does that mean? The direction of electric field randomly changes and very frequently. So at a certain instant electric field may be in one direction, the very next instant it can be in some other direction which is randomly changing with time. That is known as unpolarized light. And if you let these things pass through the polarizer, then what you get is linearly polarized light, because the electric field is now having a very specific direction. Apart from these, you also have circularly polarized and elliptically polarized light, but we will be doing some experiments with unpolarized and linearly polarized light. So here is a polarizer sheet, looks like just a plastic sheet, but it has been made in such a way that if unpolarized light goes, the emergent light will be polarized. There is some specific direction in this film, in this plate, in this sheet, and if electric field is parallel to that specific direction, it will go through, and if it is perpendicular, it will be stopped, and that direction is fixed with respect to this boundary of this plate. We have a laser source here, that usual laser pointer, not a very good laser, but still, and here it is. You can see this light from laser, and if that light goes through this polarizer, you can see some intensity is coming. Electric field does have some component which is going through. And now let me rotate this polarizer sheet. If I rotate the polarizer sheet, that specific direction also will get rotated, and you see if there is some variation in intensity seen by the camera, and here you see the intensity is very low. So, first thing is, it tells me that this light which is falling on this sheet is polarized to a good extent. Its electric field is not randomly changing in direction. If it changes randomly in direction, then some of those electric fields will be, or the components will be along that specific transmission direction, and the intensity will always come. But here it depends on the orientation. If I rotate it further, again you see the intensity has increased. So, that explains the working of the polarizer, as well as it tells me that light from the laser source, at least the one which I am using, is largely polarized. Its electric field has a specific direction, and in this orientation where the intensity is maximum, the electric field is parallel to that transmission direction. This is an LED that is glowing, blue LED, very famous word nowadays, and if I let it go through the polarizer, and the camera is seeing through the polarizer, so the light transmitted by this polarizing sheet is falling on the camera, and if I rotate, the intensity is almost the same, at least in the limit of resolution that we have. The intensity is not changing as I rotate the polarizer sheet. So, that tells that LED is giving me unpolarized light. So, although there is a specific direction in the sheet, but since the electric field of the incident light is randomly changing its direction here and there, all orientations of this sheet are equivalent. So, it tells me that LED is giving me unpolarized light. Let us look at some other sources. A CFL bulb, this is CFL tube, and you can see the intensity now, and if I rotate the polarizing sheet, you see that intensity is almost the same. CFL also sends me unpolarized light. Here is a torch bulb, filament bulb, and you see this filament bulb, light going through the polarizing sheet, going into camera, and you can see the intensity, and I am rotating, and you keep watching the intensity of that bulb captured by the camera, and you see that the intensity does not vary as far as we can distinguish. Now let me look at the light source on the roof, and if I bring this polarizer sheet in between and rotate, no change in intensity. So the light coming from this source fixed at the roof is also unpolarized. Now the same light source is illuminating this table. So let us look at this table. I put this polarizing sheet here, so that light going into camera has to pass through the sheet, and now I am rotating it. Is there a change in intensity? Has the intensity gone down? I keep rotating it further. Is it increasing again? High intensity here. The table is very clearly seen, and now the intensity is going down. Now the intensity has gone down. It has gone down considerably. So what does this say? The light coming from the source is unpolarized, but when the same light falls on the table and reflects and goes into the camera, becomes at least partially polarized. You had seen how the appearance of this table surface changes once I put the polarizer in between and rotate the polarizer. This is because the unpolarized light from the light source in the roof falls on the table surface and reflects. Now reflection, although you can find the path, the angles etc. in ray optics approximation, but if you want to talk about the fraction of intensity reflected, you have to again go for the wave property. Light is an electromagnetic wave, it has got electric field vector, magnetic field vector. The electric field vector has a direction, and if this electric field has a direction which is in the plane of incidence, then the rules for intensity reflected is different, and if it is perpendicular to the plane of incidence, the rules are different. Now it so happens that if the electric field is in the plane of incidence and the angle of incidence happens to be tan inverse of the refractive index of the surface on which it is falling, on the medium on which it is falling, then the reflected intensity becomes 0. So when it reflects from the table, some kind of that effect is there. In the reflected light, one component is dominant over the other, and if my polarizer sheet cuts that component, then you see a darkish surface, and if the polarizer sheet allows that component, then you find that yes, the surface is very well seen. So let me do one more experiment based on this. Now here you can see a flower, and the camera is looking at the flower, and we put a glass sheet on this. Ranjit, please place the glass sheet, and in the camera you see almost nothing, because sun is falling on this glass and is getting reflected and going into the camera, and hence the flower is not seen in the camera. Okay. So, I have a polarizer sheet in my hand and I am going to bring this sheet in the path of the reflected light which is going into the camera. So, you can see I have put this sheet here and now I am rotating this sheet, and as I rotate the sheet, at some point of time you can see the flower. The sun is still falling on the glass plate. If I remove the sheet from here, it is like this, and if I bring the sheet in this particular orientation, you can see the structure of the flower, the colors very nicely. If I rotate the sheet is still there in the path, but in the orientation, a different orientation, and you do not see the flower, and only in this particular orientation you see the flower. I have shown you that light coming from the CFL is unpolarized. The electric field changes its direction randomly, and therefore, if I bring the polarizer and rotate, no variation in intensity is seen. But another important point is, whatever light is coming through this polarizing sheet has now become polarized, because it will allow only those electric fields which are parallel to the transmission axis. If the electric field is at some other angle, only the component parallel to the transmission direction will go through, and whatever comes out, it has a specific direction of electric field which is parallel to the transmission axis. And therefore, if I bring yet another polarizer here on top of the first one, with the axis same, transmission directions are same, then the second polarizer also allows the light to go through. But if I rotate that second polarizer, then the light falling on it is no more having electric field parallel to the transmission axis, and you can see as I rotate this second polarizer, the intensity is decreasing. And somewhere here the intensity is very low. Intensity is very low. The first polarizer allows electric field parallel to its axis, but that direction is not the direction parallel to the transmission axis of the second one. It is perpendicular in fact, and therefore the intensity is low. You can see the intensity is very low somewhere here. And if I rotate it further, the intensity again increases. See, I am rotating it further and the intensity again increases. And once the two polarizing sheets are having parallel transmission axis, the intensity is maximum.